Alright, today in advanced geometry we're going to talk about quadrilaterals, trapezoids, and kites and learn some properties of them. What you see here, this big old sheet with all the entire hierarchy on it, that's like the entire back page of your test. So what we're going to do this whole chapter is work our way through this hierarchy, and then on the test you'll be expected to have all that information memorized. So let's just get started. Here in a quadrilateral, the first thing we'll put underneath it is the definition, which of course is a four-sided polygon. I know I didn't give you much room to write, so just kind of squeeze that in there. And then, what I want to know about each one of these quadrilaterals is how many symmetry lines it has and where they're located, and tell me about the diagonals, and tell me any other basic properties about them. So when it comes to what a symmetry line even is, a symmetry line is like if I was to put this line down the middle of this quadrilateral, is everything on the left side exactly the same as on the right side? Well, no, that's not a symmetry line, but it doesn't just have to be straight up and down. It could be anywhere. But for just a plain Jane quadrilateral, there are no symmetry lines whatsoever, right? It's got to be something fancier for there to be symmetry lines. When it comes to the diagonals, if I was to call this point A, B, C, and D, the diagonals are segments that connect two points that were not already connected. So like segment AC and segment DB are the diagonals. And I want to know if they are perpendicular to each other, which these are not. I want to know if they bisect each other, meaning cut each other into two equal pieces. These do not. And I want to know if they were equal to each other in length, and these are not. So when it comes to the diagonals of just a plain Jane quadrilateral, we just say that there's nothing fancy about them. The only true thing that we know about a quadrilateral besides its definition is that if it's a convex quadrilateral, the sum of all the angles will add up to equal 360 degrees. If it's convex, it's possible for this thing to dent in, then that wouldn't happen. So we'll get that copied down underneath quadrilateral. You can always pause the video if I'm going a little too fast. As we move to a kite, remember the definition comes first, and that's the one that's a little more complicated. It's got two distinct pair of consecutive sides equal, and if you see me abbreviate, you can abbreviate also. And I'm fine if you need to go out of bounds a little bit here, I mean, I know it's hard to write in that small space. So when it comes to a symmetry line of a kite, though, it will have one symmetry line through what's called the ends. So what you have to do is tell me how many symmetry lines there are and where they're located. So if you look at this kite that I have drawn to the right here, here's the symmetry line. This guy, everything to the left of it is exactly the same as everything to the right. The symmetry line of a kite goes through what's called the ends. Out of points A, B, C, and D. Out of those 4 points, you can see B and D are the ends of the kite. And that means that A and C are what you call the non-ends. So if B and D are the ends, then A and C are the non-ends. So there's one symmetry line for a kite. That's important information right there. When it comes to the diagonals, here I will draw the diagonals in. As you can see, I already had one in that red segment right here, but here's the other diagonal. Pretty much looks like they intersect at a 90-degree angle, so they are perpendicular to each other. But what ends up happening, though, is, see, the red guy, it totally cuts the green guy into two equal pieces, since the red one's the symmetry line, right? So the red one bisects the green one, but the green one does not cut the red one in half. So the diagonals of a kite do not bisect each other, and they're definitely not equal to each other. So out of those three things that I'm concerned about, the diagonals are just perpendicular to each other. And that's one of the big keys to how we're going to do a lot of these homework problems, is symmetry lines and diagonals. Symmetry lines and diagonals. And then the property that we'll write down for a kite is that the non-end angles are equal. And hopefully that makes sense. If there's a symmetry line right here, that the measure of this angle should be the same as the measure of that angle. So the non-end angles are equal in a kite. So I gave you another practice worksheet. Go to the back side of it, which is about kites. Sorry, I put that on the back side, not the front side. But they want us to do a few problems about kites. So what we need is this in front of us so we can see all of the information that we know about kites, and we'll do these problems. So first, if you only look at the picture, you're probably not going to be very well off. You need to read the problem and they tell you that it's a kite, right? They say WXYZ is a kite. Also remember, when they name a polygon, they put the 4 letters or however many letters there are in what's called consecutive order, WXYZ. They went around the clock like that. They can't just jump around and call it like WYXZ or anything like that. That's not the right order. So the order is very important of how they name that thing also. And you'll see why as we do some later problems. But they ask us to find the measure of angle Z. We're just going to find the measure of everything. Here's what I need to think about. Symmetry lines and diagonals of a kite. Well, they give me these 2 angles. I really care about where are the ends of this kite. Out of W, X, Y, or Z, which 2 of those 4 are the ends? Since this property right here says that the non-end angles are equal, and these angles right here are not equal to each other, they must be the end angles. So that means that W and Y are the ends of this kite. So, because of the non-end angles being equal, if we call this angle X right here, that's got to be angle X right there. So, the other property that we know is all 4 angles should add up to 360. Even though that wasn't in kites, it was under quadrilateral, so all 4 of these bad boys add up to 360. So 2x plus 140 should equal 360, right? 2x's plus 140 equals 360. Then we could subtract 140 from both sides, and then divide by 2, and get x equaling 110. And then we can answer the question. They said find the measure of angle Z. That's going to be 110 degrees. Here, they tell me this guy's a kite, again also. The ends would be A and C, just by looks. And first, let's go with the symmetry lines. Isn't this guy right here going to be the symmetry line for that kite? So, if this angle is 39 degrees, then that angle's got to be 39 degrees based on the symmetry. And if this guy is 67, then this guy's got to be 67 degrees. What you got to realize is this dude is not 67 degrees. That doesn't work right there, because this diagonal right here is not a symmetry line. So we found some angles, but see, that's not good enough, because look back to the sheet with the kite information on it and tell me about the diagonals of a kite, right? It's about symmetry lines. There, I've used the symmetry line. Now tell me about the diagonals. It says that the diagonals are perpendicular. So that means that if you have a 90-degree angle right here, and I think it's helpful to put 90 on all of these, because we can still find more angles, because in this picture, geometry's best friend shows up. We get ourselves the good old triangles. There's 4 different triangles in this picture. So, as you can see, here's a triangle. And I know 2 angles. I know this is 39 degrees. I know that's 90 degrees. So it's possible for me to find this third angle, because all 3 have to add up to 180. So 39, 90, this has got to be 51 degrees. And then based on symmetry, this has got to be 51 degrees. And then over here, I got a little right triangle here also. That's 90 degrees. That's 67 degrees. So what's left for this is going to be 23 degrees. So knowing that the diagonals were perpendicular really helped us. But see, that's just all the missing angles. Now we got to find all the missing side lengths. So it kind of boils off of symmetry again for starters. If this guy is 5, then shouldn't this guy right here be 5 based on symmetry? And then of course we use our friend the right triangle again. These weren't just plain old triangles, these were right triangles, and I know 2 sides in that right triangle, so I can find the third side if I call that x right there by the Pythagorean theorem. So remember that the hypotenuse is always the side that goes by itself. So 5 squared plus 12 squared should equal x squared. And then we can do this whole thing without a calculator. 12 squared is 144. Adding those together, you get 169 equals x squared. And then 169 is a perfect square. If we square root it, we get plus or minus 13. But we got to throw out the negative, because negatives just don't make sense for a distance. So we'll say that that is 13. And then based on symmetry, that is 13 also. But we have other right triangles. We've got this guy right here. We just can't call this side length x because we've used x already. We've got to use a different variable, so I'll call that y. And 4 squared plus 5 squared should equal y squared. This was the hypotenuse. That's why it went all by itself on one side of the equal sign. 16 plus 25 equals y squared. And add those together and get 41 equals y squared. And 41 is not a perfect square, so when we square root both sides, we'll just leave it the square root of 41. So kites, a lot of work on kites. It all boils down to the symmetry lines helped you with finding some angles, and the diagonals are perpendicular, which gives you a bunch of right triangles in the picture. Here they say find the measure of angle JRK. So from J to R to K. Well, this is a kite, right, because they say so. So that's got to be 90 degrees. Put it in the picture. If the distance from R to J is 3 and the distance from R to K is 10, find the distance from J to K. What I'm going to introduce to you now is how to probably do this the officially right way. Instead of making up a variable for this like X or Y or something like that, we're just going to call it by its name. This is the hypotenuse of that right triangle, so we'll do Pythagorean theorem. We'll do 3 squared plus 10 squared equals the distance from J to K squared. That way when we're done solving this, we can actually just see what the answer is. So 9 plus 100 equals the distance from J to K squared. Add those together. And then 109 is not a perfect square, so I will square root both sides and get the distance from J to K equals the square root of 109. Nice. And then I had some typos in this last problem on this side. It says when ABCD is graphed, a kite is formed. Cross out the word quadrilateral, put kite. Show that ABCD is a kite by showing that its diagonals are perpendicular. This is where I'm very picky about how we label our work, because what we want to do is we have coordinates. We need to show that the diagonals are perpendicular. So how we'll do that is we'll find the slopes, and if the slopes are opposite reciprocals, since we're on a graph here, then we know that those things are perpendicular. The question is, if the guy's named ABCD, what are the diagonals? Well, since they have this in order, ABCD, we know that A and C, which are not already connected, in consecutive order, they got to be some diagonals. So let's find the slope of segment AC. This is what I'm talking about when it comes to how to label your work. And segment AC, that will definitely involve points A and C. To find the slope, remember the y's are on top, so it's -3 minus 6 and y2 minus y1 over 8 minus 2. And then just keep working straight across. You get a -9 over 6. Reduce and get -3/2. Now, before I even get started, if these were truly perpendicular, the other diagonal is going to be segment BD. Its slope should be the opposite reciprocal of that, which is 2/3. So when it comes to segment BD, I will find its slope next. If I could write. Y2 minus Y1 over X2 minus X1. I missed that, my bad. 1 minus 7. Make sure you get the right points. And then you'll get -4 over -6, which a negative over negative is a positive 2/3. So, booyah, now let's answer the question. We will say that segment AC is perpendicular to segment BD because they have opposite, which I'll let you abbreviate, reciprocal, which I will not, I'll let you abbreviate, reciprocal slopes. So we answered the question there also. So back to that hierarchy deal, and now let's fill out our information about a trapezoid. Its definition, remember, it's got at least one pair of parallel sides. It's got at least one pair of parallel sides. And when it comes to symmetry lines for a trapezoid, it will have none. And there is nothing fancy about the diagonals either. They are not perpendicular to each other, they do not bisect each other, and they're not equal to each other. The only thing we know about a plain old trapezoid besides its definition is that consecutive angles between parallel sides will be supplementary. Consecutive angles between parallel sides will be supplementary. So there are 4 angles in this trapezoid. Here's the parallel sides, the green guys right here. These red guys are not parallel to each other. Now when it comes to consecutive angles, you got like angle 1 and angle 2 are consecutive angles, angle 2 and angle 3 are consecutive angles, 3 and 4, and 4 and 1. Let's just pick on angle 1. 2 angles that are consecutive with it are angle 2 or angle 4. One of these sets of angles is between the 2 green parallel sides, and one of these sets is not. You see how 1 and 2, they're between the parallel sides, and 1 and 4 are between the red sides, which are not parallel at all. So consecutive angles between parallel sides are supplementary, meaning if this was 100 degrees right here, then this guy would have to be 80 degrees. And over here, same thing, like if this is 120 degrees, then this has got to be 60 degrees. But in no way, shape, or form do these 2 angles add up to be 180 degrees, because they're not between parallel sides. The red dudes are not parallel to each other. So consecutive angles between parallel sides are supplementary. For an isosceles trapezoid, I get kind of emotional about its definition. If you have trapezoid's definition, you should not get isosceles trapezoid definition wrong, because it's the same thing over again with a little bit of extra. It's got at least 1 pair of parallel sides, and base angles equal. At least 1 set of parallel sides, and base angles equal. When it comes to symmetry lines, there's one symmetry line for an isosceles trapezoid. It's the perpendicular bisector of the bases. The bases are the 2 parallel sides. So the perpendicular bisector of bases, remember, tell me there's 1 and then say perpendicular bisector of the bases. The bases are the parallel sides. So you can see when I put these in here that this is definitely not a symmetry line for it. And this guy is not quite the symmetry line, but this dude is. This blue line, that perpendicularly bisects the bases to where it goes right smack dab through the middle of that top base, and it went through it at a 90 also. If it perpendicularly bisected this base right here, it will also do the same to that thing right there. So the symmetry line of an isosceles trapezoid is the perpendicular bisector of the bases. The diagonals of an isosceles trapezoid are equal to each other. So as you can see when I have them drawn in, the red guy and the blue guy are the same length. They do not intersect at a 90, so they're not perpendicular to each other. They do not cut each other into 2 equal pieces, so they do not bisect each other, but they are the same length. That's it. They're just the same length. And then the property that we know is that these legs are equal. If these guys are called the bases, then these other 2 sides right here are called the legs. And based off the symmetry line, again, obviously those 2 have to be the same. So we just kind of write that as a special property, that the legs are equal in an isosceles trapezoid. So back to our worksheet, and we're going to skip this first problem. We didn't do it in class, so we're not going to do it here. But let's go to this first problem right here. It says find each measure. We're just going to find everything that we can and put it in the picture. First question, is this a trapezoid or is it an isosceles trapezoid? And since it's got at least 1 pair of parallel sides and base angles equal, it's an isosceles trapezoid. What we can do is use the properties of trapezoids and isosceles trapezoids, because it's all going to work for this bad boy. Here's some parallel sides. Aren't these 2 consecutive angles right between them? So they have to add up to be 180 degrees. If this is 125 degrees, this has got to be 55 degrees. Because those are consecutive angles between parallel sides, so they got to be supplementary. Then, by way of arc marks, if that's 55 degrees, this has got to be 55 degrees. And again now, here's some consecutive angles between parallel sides. So if this is 55, this has got to be 125. So, isosceles trapezoid there. This guy is just a plain old trapezoid. It's got at least one pair of parallel sides, but it doesn't have base angles equal, or they didn't tell me that these legs were the same. That's another way that you can see in a picture if it's an isosceles trapezoid, but they didn't have that, so this is just a plain old trapezoid. The only thing we can find is the consecutive angles between parallel sides being supplementary, so that has to be 140 degrees. And that's it. That's all we can do for that one. And now the coordinate geometry comes in to where here's what they want us to do. They got a quadrilateral with us and they gave me some vertices. They want us to verify that it's a trapezoid, so we'll do that. They're basically saying, dude, this is a trapezoid, show me, right? So verify that it's a trapezoid. Then after you do that, check to see if it's an isosceles trapezoid or not. So why don't we plot those 4 points and connect them together with your straight edge. Why don't you pause the video and get that done. And once you get them plotted, looks like so. The whole point of us plotting this is so you can see which two sides do you feel are parallel, because they say show me this is a trapezoid. To be a trapezoid you got to have at least one set of parallel sides, so I gave you the little graph right here so you don't have to find the slope like 4 different times. That would just be annoying to find all 4 segment slopes, when really, now that we see the picture, don't we want to see if those two dudes are parallel. Now I'm not going to let you count rise over run because the graph will go away here eventually. So we need to find the slope and show me. That's the whole idea. Prove to me algebraically that this is a trapezoid. So we need to find the slope of segment AD. So I'll do that. Here's A, here's D, and that's going to be y2 minus y1 over x2 minus x1. So minus a minus. Right? This is where our signs really get picky, which is 2 over 1. So the slope of segment AD was 2 over 1. Now since we want them to be parallel, don't we want to get the same slope for the slope of segment BC? So, and it's got to happen, right? They're telling you basically in the instructions that it's a trapezoid, so it's supposed to happen. BC. So that's these guys right here. I will do negative 2 minus 2 over 1 minus 3, which is negative 4 over negative 2, which is 2 over 1. So I got the same slope. That means that we'll say segment AD, I can't write, segment AD is parallel to segment BC. And then we need to explain why, and we can just do that in 2 words because they had the same slope. Boom. So verify it's a trapezoid. Done, because we got at least one set of parallel sides. Then determine whether this is an isosceles trapezoid or not. And there's many ways to do that. Here's how we're going to do it. We're going to do it by finding the diagonals and seeing if they're equal to each other, because that's one of the properties of an isosceles trapezoid, that the diagonals are equal. So we use the distance formula, and it's time we get a kind of skip some steps in the distance formula. So you can also look at the picture and just be like, I don't think that this is going to be an isosceles trapezoid, just by way of looks. But it doesn't really matter what it looks like. It matters what you get with the algebra. So the diagonal, segment AC is a diagonal, so I want to find the distance from A to C. So I will do that. And of course, I've scolded you enough about how to write your distance formula stuff. So distance from A to C. Like I said, we're going to skip some steps. Here's exactly what I want you to show. You will show me that you're going to put the numbers in the right place. You're going to subtract your x values from each other and square them, and then add to it the y values subtracted from each other. So 1 minus minus 2, which turns into a plus 2 squared. So that's the setup for the distance formula. Then you'll just keep working down, and we're going to kill 2 birds with 1 stone if you can handle it. And if you can't handle it and you don't want to skip steps, then don't skip steps. But check this out. In the parentheses is negative 1 minus 1, which is negative 2. And that needs to get squared. So negative 2 squared is 4. Plus 1 plus 2 is 3. 3 squared is 9. So I kind of did 2 steps at 1. Now the last thing I'll do is combine my like terms underneath there and get the square root of 13. And since 13 is not a perfect square, we're just going to leave the answer like that. We're not going to try to simplify the radical, even though that doesn't even simplify in the first place. So There's one diagonal, square root of 13. Let's find the other diagonal, which is the distance from D to B. Let's do that in a new color. Distance from D to B will be using these points, so box, box, big ol' honker radical, subtract your x's from each other, so 3 plus 2 squared, and then add to that the difference of your y's, 2 plus 1, quantity squared, and then clean it up. 5 squared is 25, 3 squared is 9, you add those together, and you get the square root of 34. So now let's answer the question. They said verify that this is a trapezoid. Boom, we did that right here. Then is this trapezoid isosceles? We will say it is not isosceles. And then because, what did we find? These are the diagonals' lengths, and they are not equal. The diagonals are not equal. Boom. So that's how we're going to do those questions. What I'd like you to do is try number 4. Pause the video, graph that thing, and then determine that it's a trapezoid by finding the sides that look parallel and find their slopes, show me that they're the same, and then see if it's an isosceles trapezoid by seeing if the diagonals are equal to each other. So give the video a pause and give it a shot. There it's graphed, right? And it looks like segment JK is parallel to segment ML, so I found both of their slopes, and yes, they were the same, of -1, so I said that they were parallel because they had the same slope. Then it also, in my opinion, kind of looks like an isosceles trapezoid, so let's see if it is by finding the diagonals. This is in the way, and I didn't even skip steps when I did this, but you're fine to skip steps. I got the square root of 29 for both diagonals, so the diagonals are equal, meaning that that thing is an isosceles trapezoid. So a lot of work, a lot of work, a lot of work. There's a typo on your homework, so let me show you that real quick. On the second page of your homework, I'm on the second page, problem number 8, point B is not in the right place. If my pen would work here. Point B should not be at 1,7. Point B is at 2,9. And then also the same kind of rules applied for my typos. Change that word to kite and change that word to is. So, but B is at 2,9. That will make things a lot easier. Let me know if you need some help. I will definitely help you with the proofs. There will be proofs on the test also. So please come see me for some help, and have a good one.